Hey guys, welcome. I'm Lakshmi Maheeswar and I'm from Amrita University, Amravati campus. Currently, I'm an undergraduate student. So, we will discuss now about generalized matrix and vector interface. So, let's go into the topic. We discuss now generalized matrix and vector interface. Firstly, we discuss about the generalized matrix. Then, after we jump into the vector interface. Generalized matrix. The concept of generalized matrix refers to the matrix that goes beyond typical square or rectangular element of numbers, used to handle more complex mathematical structures and scenarios. These are the some type of generalized matrix. 1. Matrices over rings and fields, block matrix, sparse matrix, operator matrix, tensor generalization. Now we discuss some of these. Firstly, we discuss about block matrix. Block matrix are likely dividing a large matrix into a smaller, more manageable chunks or blocks. Each of these blocks can be thought of as its own smaller matrix. And by organizing these smaller blocks, we can manipulate the larger matrix in a more structured way. A block matrix is typically expressed as this, and this is the M into N matrix. Why we should use the block matrix? What are the uses and what are the advantages? Mainly, the three advantages are efficiency. Working with a large matrix is often more efficient to treat section blocks as once rather than dealing with each individual element. For instance, multiplying two large matrices by multiplying blocks can reduce computational complexity. Structure preservation. Sometimes the block structure reveals something about the underlying problems. For instance, in creation physical system, blocks may be represent interaction between distant subsystems. By organizing things into blocks, we can keep the interactions within the subsystem clear and separate from the overall system. Next one is parallel computing. In computer science, dividing a problem into smaller blocks allows for parallel processing where each block can be processed independently on different processors depending on computation. This is the example. Matrix A is of the size 4 into 4 and matrix B is of size 4 into 4. We are dividing this 4 into 4 matrices into a smaller chunks where W1, Y1, X1, Z1 are the subparts of the A and W2, Y2, X2, Z2 are the subparts of B, and we are adding individually according to the places. The result of this individual matrix is the final result of these adding the matrix. This is how we divide the matrix into chunks. We perform the operations separately. Now we will go to the sparse matrix. A sparse matrix is a matrix in which most of the elements are zero. Due to the large number of zero elements, storing sparse matrix in a standard 2D array format results in significant memory wastage. To address this, specialized representations are used to store only the non-zero elements of the matrix, optimizing both space and operations. Two common representations for sparse matrix are three-column representation and second one is compressed sparse row. First we discuss about three-column representation. In this, we represent the matrix in the form of table where first row index indicates the row index where the non-zero elements, and second is column index where non-zero elements are there in which column and the value associated with it. Here in this example, in first it means in zeroth row there is an element. In this row there is an element, so 0, it is 0th row, and 1 0 1 2, and second column there is a non-zero element 0 2, and the value associated with these positions is 3. In second row, first element is 5. Similarly, this is how this table is formed. This is one of the form represents the space matrix, and second one is compressed space row. Here also the values stores all non-zero elements of the matrix in row-wise manner. Column indicates store the column indices corresponding to each non-zero element in the value array, and row pointers store the starting index in the values array for each row of the matrix. In this example, the values are 3 5 7 9, and the column indices are, this is the second column 3, and this is the first column, and this is the 0th column, and this is the third column. And how the row pointers are there, initially we take it as 0, then after it, in first row there is a one element, so this is incremented by 1. In second row there is another element, so it is incremented by 2. In third row there is two elements, so it should be incremented by 2. So 2 plus 2 equal to 4. This is how. Now we will discuss vector interface. Vector class is a part of collection framework and is used to implement a dynamic array that can grow or shrink in size. The vector class is very similar to an array list, but with a key difference: synchronization. While array list is not synchronized, that is, it is not thread safe by default, vector is synchronized, meaning that it is safe to use in a multi-thread environment. The basic properties of vector. Firstly, dynamic array. The vector class implements a dynamic array that grows when the current capacity is exceeded, just like the array list. However, unlike arrays that have a fixed size, the vector can expand dynamically, allocates more memory when required. Second one, thread safe. Vector is synchronized by default, which means it can be shared safely among the multiple threads. This ensures that two threads cannot modify the same vector object at the same time, avoiding data corruption. Third one is growth factor. When a factor needs to grow, it increases its size by a creation amount, which is typically double its current capacity. You can also specify a custom capacity increment when creating the vector, which controls how much extra space is allocated each time is grown. Fourth, legacy class. Although vector is still a part of the Java collection framework, it is considered a legacy class. Most modern Java application prefers using array list and explicit synchronization via classes like collections, synchronization list, or copy online or on-write list from multi-thread scenarios, because vector default synchronization can add unnecessary overhead when thread safe is not added. And also there are constructors in vector class. Actually, there are three constructors, where default constructor having an initial capacity or a default capacity 10. If we want to increment it, we can increment the capacity where 10 into 2, and second one we can specify. To overcome some problems in second con- constructor, we can initialize the capacity of the constructor initially, where it is also, if we need to extend capacity of the constructor, we need to multiply the capacity into 2. By overcoming this, there are another constructor where the initial capacity can be given, and also the increment size also can be given. This is the most efficient construction, and this is about the generalized matrix and vector constructions. Thank you.